So let's start talking about our sorting algorithms. We need to start off by having a general understanding of what sorting is. And I just want to be clear, and I want everybody to be on the same page, even though I'm sure everyone already has a good idea of what it means to sort something. But again, just so that we are all on the same page, sorting is when we place items in either ascending or descending order. So let's depict what that means. So we'll start off and we'll have a vector of 4, 3, 1, and 2. So it's completely unsorted right now. Unsorted. If we want to go into ascending order, we have 1, 2, 3, and 4. And that would mean that our vector is now sorted in ascending order. So this is ascending. So ascending means that our values are in increasing order. Therefore, if we wanted to do a descending sort, our values would decrease as we sort them out. So they would be descending. So what is the purpose of sorting values? When we have our items sorted, it's going to allow us to do a much quicker lookup of an item. And there are different algorithms that we can use to sort a series of values. And in this lecture, we're going to start off by talking about selection sort. So let's start to look at what selection sort is and how we can perform it. So we have selection sort. So to start off, we will use the exact same vector of values that we had above of 4, 3, 1, and 2. So we want to use selection sort to sort these values. So we'll do a quick iteration of sorting this using selection sort, and then we'll look at some pseudocode, and then we will do one more selection sort as an example. So what we'll do is we'll start here at value 4. And we'll say that value 4 is our smallest value. So we will say smallest value is currently 4. And now we'll look ahead. So we will say I plus 1, I for index. So we're currently at index 0. And we will look through the rest of the array and find the smallest value. So 3 is smaller than 4. So our new smallest value is technically 3. But then our next index, we have 1. So our new smallest value is now 1. And then we have 2. And 2 is not less than 1. So what we will do is we will swap 1 and 4. So our new array looks like 1, 3, 4, and 2. So now that we have done one iteration through the array and we know that 1 is in the correct spot, we will now start with this index. And then this will be I plus 1. So now we have 3. So our smallest value now is 3. Actually, we'll do it this way. So we went 4. We had 4, 3, 1. So now we will have our smallest val here, and it is currently 3. So we look at 4. 4 is not less than 3, but so now we look at 2. 2 is less than 3. So we can get rid of 3, put 2 there, and now we will swap 3 and 2. So now we have 1, 2, 4, and 3. So we know that 1 and 2 are sorted now. So we are back to looking at 4, and then this is I plus 1. So in this case, our smallest val is 4 again. When we compare 4 and 3, we see that 3 is obviously less, so we swap them now. And we have 1, 2, 3, and 4. So now our vector is sorted in ascending order, just like how we wanted. So now that we have a general idea of how selection sort works, how could we code this out? Well, we could say for I in 0 to size -1, and then we want for j, so I in this case is referring to where we start at. So this was I here, this was I here, I was here, and then we were sorted. And then j was always one step ahead. So this was j plus 1, j plus 1, j plus 1. So now we have for j in 1 to size, so that gives us the correct index that we are looking for. And then we want to just do our simple checks. So we have our smallest value. Well, let's get rid of that. If smallest val is greater than I, then we want to make our small value equal to I, because then we know I is less than our smallest value. And then when we have iterated through all of the elements, we want to simply swap I in the smallest value. And that is all we really have to do for this code to work. We just go through each iteration and we want to find the smallest value and then swap them, because then we know that that index is completely sorted and in the correct order. So when we're looking at this pseudocode, we see that our big O notation, just keeping this in mind, is going to be O of n squared. We have two nested for loops that are iterating the size of our vector. So we know that our big O is going to be n squared. So not the most performant method, but it does the job. So let's do one more example of this. So let's get down here some, and we will do a new array of values 5, 10, 1, 4, and 11. So this is our new vector, and we're going to keep our algorithm, our pseudocode up here in mind. So this is going to be our I value, and this is going to be our j plus 1 value, which means our small val in this case is equal to 5. So j plus 1 is 10. Is 5 greater than 10? No. Is 5 greater than 1? Yes, it is. So now we will replace the smallest value with 1. Is 1 greater than 4? No. Is 1 greater than 11? No. So now we do our swap. So now we swap 5, because that was I, and our smallest value of 1. So our new array now looks like 1, 10, 5, 4, 11. And now that we know that 1 is completely sorted and definitely in the correct order, our new I is now 10, and this is our j plus 1. So our small val is equal to 10. Is 10 greater than 5? Yes, it is. Is 5 greater than 4? Yes, it is. Is 4 greater than 11? No. So now we want to swap 10, because that is I, and our 4. So now we have 1, 4, 5, 10, and 11. So now this is our I, this is our j plus 1. We do our comparisons. We see our small val is equal to 5. Is 5 greater than 10? No. Is 5 greater than 11? No. So now we don't have to do anything. Increment up. So 10 is now our I, and 11 is our j plus 1. In this case, our small val is equal to 10. Is 10 greater than 11? No. We now hit the end of the array. So we know for sure that our array is now sorted. So now that is how selection sort works. We are now going to implement this algorithm in our next lecture. And if you have any questions at any point, please feel free to ask them in the Q&A section. Now that we are comfortable with selection sort, we can begin implementing our own solution to the algorithm. So to start off, we know that we need a vector that we are going to want to sort. So we will say let mut array, and we will give it a type of vector storing I8s, and then we will create it. And we want to use the same values that we used in the previous lecture. That way we can verify our results and understand how our algorithm was able to sort the values in ascending order. So something else that I want to do is I want to print out the values before and after we sort, just to make sure that everything was done properly. So we have before sorting, and we were going to pass in our array. And we'll copy and paste this, and we will change this to after sorting. So you can see by my print line statements that I'm using the same variable in every location. So that means that I am going to use selection sort, and I'm going to pass in a mutable reference to our array. So now we can begin implementing in our function called selection sort. So we're going to pass in our array. We know it's going to be a mutable reference of a vector that is of type I8, and we want to return our vector that is an I8, that contains I8 values. So we looked at the pseudocode and we knew that we had 2 for loops. So I will go ahead and start with the first one. So we will start at index 0 and go to our array length -1, which is following what we did in our pseudocode. And now we want our smallest variable, or value, excuse me, to be equal to I, and we need it to be mutable because remember, if an index is less than our current smallest, then we need to update our current smallest value. So therefore it needs to be mutable. That way we are able to update it. So now we're going to do I plus 1 all the way to our array dot length again, but this time we're going to go to the end of the array. And so now we can do our checks. So if array of j is less than our smallest value, is less than the array of smallest, then we want to set smallest equal to j. And now, once we exit out of the loops, we want to swap, and luckily there is a swap function for us in the vector methods. So we want to swap our smallest and our I value. And now we want to return our array, and we have to say array to vec. So now we have our array and our selection sort set up. So let's execute this code to make sure it runs correctly. So we see before sorting we have 4, 3, 1, and 2, and then after sorting we have 1, 2, 3, 4. So that looks correct. Let's do one more test case to make sure everything looks good. So we will say let mut array2 of vec I8 equals to vec, and let's do our second test case that we did in the previous lecture. So we have 5, 10, 1, 4, and 11. And now we want to print out the same messages as before sorting. And we're going to do our second array. We will call selection sort on a mutable reference again to our array2. And now we will do our print line again and say after sorting array2. So we now expect this to be printing out two arrays for us. So we have our first array, which we already know is correct, and now we have our second array of 5, 10, 1, 4, and 11, and we see that after running our selection sort algorithm we have 1, 4, 5, 10, and 11. So we are confident that our selection sort algorithm is correct and is correctly sorting the vectors we pass into ascending order, so into increasing order. So we are confident that our solution is correct. So in the next section we will continue on learning about additional sorting methods, and remember, if you have any questions at any point during any of the lectures, please feel free to ask them in the Q&A section. Now that we have a good understanding of a sorting algorithm like selection sort, we can continue on and learn additional sorting algorithms. In this lecture, we are going to begin looking at what bubble sort is. And bubble sort is one of the simplest sorting algorithms because it just repeatedly swaps the adjacent values if they are in the wrong order. So it's not going to be super performant for large data sets, but it's still a good sorting algorithm that we can evaluate and learn. So we'll create ourselves an array here, and we'll give it 5, 4, 1, 3, and 2. And remember, what we're going to do is sort adjacent values if they are in the wrong order. So we see here, so we'll start at 5, index 0, and we see that our adjacent value is 4, so now we can swap 5 and 4 and then leave the rest of them the same. And we're still on value 5 because we have not iterated through the entire array, so now we're still at 5, and we're going to swap now with value 1 because 1 is less than 5. So now our array is 4, 1, 5, 3, 2. And again, since we haven't completely iterated through the array yet, we are still on value 5, so now we will compare 5 and 3. 3 is less than 5, so now we will swap 3 and 5. So now we have 4, 1, 3, 5, 2. And now that we're almost at the end of the array, we have one more check that we need to do, and we need to check if 5 is less than 2, which it is. So now we have 4, 1, 3, 2, and 5. So now we have completely iterated 5 through the array, so now we know that index 5 is in the correct spot. 5 is in correct spot. So now we're going to go back and we're going to start over with 4. So now we're here at 4 and we're going to compare it to 1. So we know that 1 is less than 4, so now we go 1, 4, 3, 2, and 5. We're still at 4, so now we compare 4 and 3, so we have 1, 3, 4, 2, 5. So you're starting to see why this algorithm might not be the most efficient one of all the sorting algorithms that we will learn. So we're still at 4. So 4 is less than 2. So 1, 3, 2, 4, 5. We see that we know that 5 is in the correct order already. So now we're done with 4. So now you're quickly starting to see the pattern here. So our next value is 1. We compare 1 to 3, 2, 4, and 5. So now we know that 1 is in the correct spot. So now we compare 3 and 2. So we know that we need to go 1, 2, 3, 4, and 5. And now we have our sorted array. So we are now done with sorting this array. So again, now you can see why it is not the most efficient algorithm, but let's look at some pseudocode to see what it would look like. Oop, not a B. So we want some pseudocode. That way we can have a blueprint for what we want to code when we go to do our implementation. So we know that we started at iteration 1, so this would be one for loop. So we'll say for I in 0 to size -1, and then we're comparing it with all the elements adjacent to it. So we're going to need another for loop, so we'll say for j in 1 to size -2, and then we will do our compare j to I, compare j if it is greater than j plus 1, and if it is, then we want to swap j and j plus 1. And that is basically our pseudocode for this. So let's do one more example. That way we make sure that we have a good understanding of how this algorithm works, now that we kind of know what the pseudocode is. So we will do an array of values of 5, 1, 4, 2, and 8. So this is our unsorted vector of values. So we will start here, and then this will be our I plus 1. So now we compare. We see that we need to do a swap. 4, 2, and 8. So we're still here at 5. Compare. We need to do a swap. Now we're 1, 4, 5, 2, and 8. So we're here still. Compare. 1, 4, 2, 5, 8. And now we know that 5 is in the correct spot because our next comparison will not yield a swap. So now we also know 1 is in the correct spot. So now we need to start here, and we will evaluate 2 and 4, and we see 1, 2, 4, 5, and 8. So that was a very simple one, and we were able to quickly see how this works. It works really well with arrays that are already kind of sorted, because as you can see, we had way less iterations needed here than we did in our array up here. So now that we have a really good understanding of how bubble sort works, let's go ahead and begin implementing this algorithm in the next lecture. In our previous lecture, we got an overview on what bubble sort is and how it works. So now that we have a good understanding of how bubble sort works, we can begin implementing our own solution for that algorithm. So the first thing I want to do is create a new function called bubble sort, and it's going to look very similar to what we did for selection sort. So we're going to create a bubble sort function, and we're going to pass in a mutable reference to a vector that's also going to return a vector. And then down here I want to go ahead and create some of our test cases. So we will say let mut vec equals vec, and then in here I want to mimic our test cases that we did in the previous lecture. So we did a 5, 4, 1, 1, 1, 3, 2. And then we also did a 5, 1, 4, 2, and 8. So now in here we know that we are going to run bubble sort, and we're going to pass in a mutable reference to our vec, and then we know that we're going to want to print it out to make sure that our vector was properly sorted. And we'll stop there for now. That way we can make sure that this at least works before we continue down here. So now up here in the function, we're going to start implementing in our algorithm. So we know that we're going to need 2 for loops. So we'll go ahead and create our first for loop, and we'll say for I in 1, 2, the array dot length -1. And since we know from the previous lecture that we actually don't use this I variable, we can substitute it with the underscore, and basically this tells our compiler, hey, we don't care about this value, so just put a placeholder in there and we're not going to reference that value at all. But in our next for loop, we do know that we're going to reference j, and j is going to go from 0 to array length -2, and then here is where we are going to do our check. So we're going to say if array of j is greater than array of j plus 1, well, now we want to do our swap. So we will say array swap, and we have j and j plus 1. And at the very end, we want to return our array, and then we will get an error mismatch down here because it says it expected a struct of vec I8, and we found a mutable reference, so we can quickly rectify that by saying to vec. And now our error is gone. So now if we come back down here and we execute our code, we would expect to see the first vector of 5, 4, 1, 3, 2 print out a sorted vector, which we see down here. We see that we have 1, 2, 3, 4, and 5. So our bubble sort is working correctly, but to verify, let's run it on our second test case of our vec2, and let's do the same thing where we just go ahead and print that out. And if we run this again, we see we have 1, 2, 4, 5, 8 printed out, which is sorted of the vector containing 5, 1, 4, 2, 8. So awesome. So it looks like our bubble sort algorithm is indeed working correctly. But if you remember from the previous lecture, there are times where our algorithm can be sorted, or excuse me, our vector can be sorted, but we're still executing these blocks of code. Therefore, we're wasting resources and time, because we could still be executing at this loop even though we know that we're sorted in here. So we can actually do a very slight little optimization here, and we can create a mutable boolean called sorted, and we'll go ahead and set it to true. But we'll also, at each new iteration of the loop, we'll make sure that it is set to true, because we know that if this block of code gets executed, then we are not sorted. So that means we want it to keep sorting out. But if this block of code never gets executed, then that means we are sorted. And since we have this boolean here and it won't get updated in here, because if it's sorted, this block of code never gets updated, then we can put an if statement down here that says, hey, if we're sorted, then I want you to break out of this loop, meaning this outer loop. And so if sorted here, this basically says if sorted is true, then break out. So with that little bit of optimization, just to make sure our code still functions as desired, 1, 2, 3, 4, 5, and 1, 2, 4, 5, and 8, those are the correct outputs. So this is an optimization that would be better for a much larger array that does sort itself, let's say halfway through. Well, we just cut the O of n squared in half. So obviously, with certain sizes of arrays, this would be a considerable performance increase. But that was just something I wanted to point out, just to kind of keep in the back of your mind as we go through these algorithms. I want you to try to think of ways that maybe you can optimize them. And if you do have unique solutions to optimize some of these arrays, because there's definitely optimizations to be made, please share them with with me and the rest of the students in the course. But hopefully you enjoyed learning about bubble sort, and we will continue looking at a few more algorithms in the next lecture. In the previous lectures, we have talked about selection sort and bubble sort, two of the easier sort methods that we can learn about. So now we're going to up the difficulty a little bit and begin talking about merge sort. And merge sort is an algorithm that is considered to be an example of dividing and conquering. So this algorithm, what we're going to do is initially divide the array into two equal halves, and then they are combined in a sorted manner, right? So we're going to divide and conquer and then re-merge them back together into a sorted final array. So let's take a look at what that means. So a very high level view, we'll say that we have an array of 4, 7, 3, 5, 1, and 2. So this is our initial array right here. So we have all of our elements, and we know that this is going to be a divide and conquer. So we will say we're going to divide right here at the midpoint. So divide the array in half. So now we have two arrays, 4, 7, 3, and 5, 1, 2. So again, this is very high level, and then we will go over a little bit more in depth after we get this high level view out the way. So now we have divided our initial array, and now we want to conquer, in a way, aka sort it, and then we want to merge it back together. So now we're going to sort it, so 3, 4, 7, and then 1, 2, 5. Again, these are their own arrays. And now that we know that these have been sorted, we want to merge it back together. So 1, 2, 3, 4, 5, 7. So now we have merged them back together, and we just executed merge sort. So how can we eloquently kind of evaluate how this works? Well, we're going to have a couple of things that we need to do. So with this being, if you might have kind of saw it, this is actually going to be a recursive algorithm, because we're going to continuously divide and conquer. So we will continuously call on one of our functions in order to continuously break down our array until we have a very basic 1, maybe 2 element array that we can very quickly sort, and then start unwinding the stack and merging everything back together. So we're going to have a base case where the array length is equal to 0 or 1. And then the steps that we want to do is we want to break the array in half, call merge sort on both halves, and then lastly, the most important part, we want to merge the 2 sorted arrays. Okay, so now let's look back at our initial example, and because we want to see how this works, obviously throughout the entire process. So let's give ourselves some additional space down here, and let's leave our base case and everything. That way we can kind of see what we're working with. So our array was what did we have? 4, 7, 3, 5, 1, 2. So we want to sort 4, 7, 3, 5, 1, 2. So I went ahead and kind of split it up because we already know that that's what we're going to need to do. So we have our 2 arrays right here. Well, what we're going to want to do here is split this array up. So our midpoint is going to be this 7. So what we'll do is we'll create an array with 4 and 7, and then we'll have 3 here. Well, obviously 3 is sorted because that is its own array with 1 element, so that satisfies our base case. But 4 and 7, we can split it up even more. We can split it up into 4 and 7. So now we know that 4 and 7 are sorted and our base case is satisfied. So we can also begin working on this one. So we will have 5 and 1, and then 2. Obviously 2 was sorted, and now we will have an array of 5 and 1 here as well. So we now have a total of 6 arrays, technically, of 4, 7, 3, 5, 1, and 2. And now that we have called merge sort on everything, we want to begin merging all of our sorted arrays. So down here we know that 4 and 7, so up as we unwind, our sorted array here is going to be 4 and 7. And now we're at the level where we have the 3, so we're going to merge the 3 back in. So now we know that we're going to have 3, 4, and 7, and that's going to be our final array there. Over here, we're going to have 1 and 5. And now we need to sort in the 2. So up here, we're going to go 1, 2, 5. So now we have our last 2 arrays that need to be sorted, and they will obviously sort to 1, 2, 3, 4, 5, and 7. So as you can see, the complexity of this algorithm is a little bit more difficult than our previous 2 in bubble sort and selection sort. But hopefully you have a good understanding of how this is going to work, and now we will begin implementing this algorithm in the next lecture. In the previous lecture, we did an overview of what merge sort is and how merge sort works. And now that we have a good understanding of how merge sort works, we can take that knowledge and begin implementing in our own solution to that algorithm. So the first thing that I want to do is set up our logic that we're going to execute in main. So we'll create our vec, and again, I want to use the same values that we used in the previous lecture. So 4, 7, 3, 5, 1, and 2. And then I want to call merge sort, and I want to pass in our vec, and then I want to print out the results of the sorted vector. That way we can confirm our work. So now we can come up here and we can begin implementing in our function. So we have merge sort, and we're going to have an array, and it's going to be a mutable. And to mix it up a little bit, I want to do a slice, an array slice. And we can use an array slice because we technically don't need to own the data being passed in. We're just wanting to point to the block of memory that it is in, which is what this array slice does. So this allows for safe and efficient access to that memory block without having to copy the data. So at the end, I would like to return a vector. That way we can view our results once we execute our code. So inside of merge sort, we want to have a base case, and we want to make sure the length of our array that's being passed in is greater than 1. That way that there's actually some work to be done. Otherwise the array has one element and it is already sorted. So we need to get our midpoint, and for us to get our midpoint we can just simply take the array length and divide it by 2, and that is going to give us our midway point in our array. And as I noted in the previous lecture, merge sort is a recursive algorithm, which is why we went over recursion in the previous section. So as you know, with recursion, in order for it to be recursive, you have to call the calling function from inside itself. So we are going to call our merge sort here, and what we're going to do is we're going to call it on the array from the beginning of the array to the midpoint. So this is going to be the left half of the array, so naturally we need to call it on the right half of the array. So we will go from mid onwards. So this is the right half of the array. So now, and just to get rid of all these errors, we're going to return our array as a vector. So now that we are actually doing the divide and conquer piece, remember, once we're done with the recursive part and our stack begins to unwind, we need to merge all the elements back together in the correct order. So for us to do this, we're going to need another function, and I'm going to call it merge, and we're going to pass in our array and also the midpoint. So merge is going to be a helping function for us that's going to take our sorted array, or take our divided arrays, and then after they're sorted, and merge them back together into one array for us. So we're going to have array that's being passed in, and again this is going to be a mutable array slice, and then we know that we're bringing in our mid variable as well, and this is going to be of type usize. So let's get the left half of the array that we passed in so that we can divide it even further, and that is going to be from the beginning to the mid, and we're going to turn this into a vector. So again, so this is left half to middle, and then we're going to say right. It's going to go from the mid onwards. So this is the right from, middle to the right half. And then we're going to create two variables here called L for left and R for right. And these are going to be pretty important for us, so we'll see what they're going to do in a second. So now we're going to have a for loop. This way we can begin merging our elements back in the sorted order. So we have, for each value in the array, if our R, so this R here, if R is equal to the right vector length, or if our L variable is less than left dot length and left of L is less than right of R. So what are we doing here? So this is obviously a pretty long if check where it is an or statement. So remember, that means either this side has to be true or all of this side has to be true. So if we are executing code in this block, so inside of this if statement, then that means R equals the length of this vector, or the L variable here is less than the left vector length, and left of this index is less than right of the right index. So we're doing a lot of checking based on where our indexes are at this level. So that would insinuate that we're going to need to update our indexes appropriately. So what we want to do is we want to dereference the val variable in here. That way we can get the raw data in there and not some memory address. And we want to check if that val is equal to left at index position L. And then we want to increment it by 1. Else, we're going to do the same thing, but this time for R. So we want to check if the val is equal to right of R, and we want to increment it by 1. So basically what we're wanting to do is figure out if the value that we are referencing in the array is part of the left or part of the right. And if it is, then we want to increment that index by 1. That way we're no longer at the beginning index of that vector. So now once we're done with that, we actually have completed this merge sort algorithm. Everything looks pretty good to me. We're doing our divide and conquers, and then we're going to begin merging everything back together. So if we come back down here, we see that we, again, earlier on in this lecture, set up this portion of the code. where we want to take our example from the previous lecture of 4, 7, 3, 5, 1, 2, and we want to sort it. So let's run this. And we see down here that we have 1, 2, 3, 4, 5, and 7. And that is exactly what we did in the previous lecture when we did it by hand. So that is the correct output. It's obviously sorted and it's in ascending order. So hopefully you enjoyed learning how to implement a merge sort algorithm in. If you have any questions about the implementation, please feel free to ask them in the Q&A section, and I will see you in the next lecture. In this lecture, we are going to start talking about quicksort. Quicksort is going to be another divide and conquer algorithm that is also going to use recursion. So kind of similar to what we did for merge sort in the previous lecture. With this being the last sorting algorithm that we are going to talk to, I am going to make this an assignment for you to try to implement it on your own. And by the end of this lecture, you will have the confidence to attempt implementing it on your own. And if you get stuck at any point, please feel free to ask some questions in the Q&A section, and I will get back to you pretty quickly on how to get unstuck and continue moving forward. After you give an attempt on the assignment, the next lecture will be my solution to implementing in quicksort. So let's start taking a look at what quicksort is and how it works. So the first thing I want to do is I want to create an array with some elements in there. So we're going to have 8, 5, 1, 2, 7, 3, and 4. And in here, we need to have something called a pivot. And there's many ways to come up with a pivot, but for simplicity, I'm going to make the last element in our array the pivot. So in this case, 4 is the pivot. And then we're going to have two variables, I and j, that are going to iterate over the rest of these elements and help us begin figuring out where this pivot goes. Because after we're done with our first iteration, we want 4 to be in the correct spot in this array. So we know that the array is going to be 1, 2, 3, 4, 5, 7, 8. So 1, 2, 3, 4, 5, 7, 8. So we want to get 4 into this spot here. This is our goal through the first iteration. But also, with 4 being here, we also want to make sure that we have 1, 2, and 3 in no particular order in these 3 spots. So when 4 is here, every element down here should be less than 4. It could be 1, 2, 3. It could be 3, 2, 1. It could be 2, 1, 3, and so on and so forth. But then the same applies for up here. We would want every element greater than 4 to already be in an index greater than where our 4 element is. That way we can begin doing quicksort on these elements as well. So that's where the recursive approach comes into. Once we have 4 in its correct spot, well, we no longer have to worry about 4, but now we can call quicksort on these elements, and then we'd be able to call quicksort on these elements. So let's go ahead and run through this real quick and kind of see what this looks like. So we will say that I is here and j is here. And what we're going to do is I is going to look for numbers greater than 4, so I greater than 4, and j is going to look for numbers less than 4. Well, luckily, we actually don't have to look too hard to find that. So we see we have I, which is a greater value than our pivot, and we have j, which is a value less than our pivot. So what we're going to do here is we're actually going to swap these values. So now we have 3, 5, 1, 2, 7, 8, and 4. So this is going to be our new array currently. And now we're going to decrement j. So j will go here. And now we're going to increase I. So remember, we're looking for values of I greater than 4 and j less than 4. So I is currently greater than 4, so we will leave that. Is j less than 4? It is not. So we will go ahead and decrement it. So now 2 is less than 4, so now we will swap these values. So our new array is 3, 2, 1, 5, 7, 8, and 4. So our j value is now where the 5 is. And now we're going to increment I by 1. Well, is I greater than 4? No. So now we will cross that out and increment it by 1. Well, now we see that I and j are at the exact same position, which now means that our pivot, and we'll just keep them circled, that way we know it's our pivot. Now we know our pivot actually goes here. So now we swap this 5 with our pivot. So now our index is 3, 2, 1, 4, 7, 8, and 5. And now if you remember at the beginning of this lecture, I said when our 4 is in the correct index, we want to make sure every value to the left of it is below 4 and every value to the right of it is above 4. And you can see that that is the outcome of our first iteration. So now we know 4 is in the correct spot. So now we would take our recursive approach and we would call quicksort here, and we would call quicksort here. And then we would keep doing that until the array is correctly sorted. And that's exactly how quicksort works. So you can see that it's a pretty efficient algorithm. So now what we want to do is we want to take a look at the pseudocode so that you can have a good idea of what we need to do in order to implement this code in. So we're going to have our quicksort function, and it's going to take a couple of parameters. We'll take our vector, we're going to take low, so the beginning of the array's index, and then the high, which is the ending array, the end index of the array. So what we want to do in here is check if low is less than high, and then we will say pi, and this is pi equals our partitioning index. So we want to do pi is equal to partition, and we want to pass in our array, our low, and our high. And then when we get our partitioning index, we want to call quicksort on the array, on the low, and then the partitioning index -1. And then we also want to call quicksort, so that would be the left side. This is the left side. Now we want to call it on the array, partitioning index +1, and then the high. So remember, this is going to be the left side, and this will be the right side. So left meaning over here, right meaning over here, and then 4 in this case is our partitioning index. And that is all we want to do for quicksort. So we'll just kind of wrap all this up right here. That way we know that this is quicksort. So we see that we have another function call in here called called partition. So now we need to create a partition, some partition pseudocode. So we're going to have partition, and partition is going to take our array, it's going to take our low, and it's going to take our high. And then in here we're going to get our pivot. So pivot is equal to, and then in our case it was our high index, so the last element, so we want to set it to array of high, and then I is going to be equal to 0 in our case, and then we will set j also to high minus 1. So now we want to implement in if j is less than, we want to find a j less than our pivot and an I greater than our pivot. That way we can start sorting them out. So if j is less than pivot and also I is greater than pivot, then we want to swap I and j, and then you want to increment I, and you will also want to increment j. And then once the index of I and j is the same, so we can say something along the lines of if array of j is less than the pivot, meaning we have passed that midway point, then we're going to want to swap I plus 1 and our pivot. That way this puts it in the middle. And this will put pivot in correct location. Let's be a little bit more specific. In the correct index. Right? So again, we're checking to see if j is less than pivot, and if I is greater than pivot, then we want to swap I and j, and then we also want to increment until this condition is satisfied. And then once array of j is less than the pivot, then you want to swap. Let's redo this part, make it a little clearer. Because if array of j is less than the pivot, that means all of our values are now correctly on the left side. So at that point, we just want to swap j and pivot. And there's other ways that you can swap here, because remember, at some point I and j are going to intersect, so that is when you want to swap. So let's just make a note of that. When I and j intersect, swap with the pivot, because then that'll put pivot in the correct spot, in the correct index. Will be in correct index. And then that's all we have to do for our partitioning function. So again, take some time to try to implement this on your own. If you have any issues, please feel free to ask them in the Q&A section, and I'll be more than happy to provide you with some assistance. And then once you have given it a go, please proceed to the next lecture while I will implement my solution to this assignment. I hope you enjoyed that assignment and that you were able to successfully come up with your own algorithm to solving the quicksort implementation. We are now going to go over my solution to the quicksort algorithm. So the first thing I want to do is set up my arrays that I'm going to test out. And again, I want to use the same values that we did in the previous lecture. So 8, 5, 1, 2, 7, 3, and then 4. And then I'm going to say let length is equal to array.length, and then we're going to call quicksort, and we're going to pass in the array 0 because that is the starting index, and length minus 1. And then lastly, I want to print out the sorted array. And now we have printed out the sorted array. So now we need to go up and implement in quicksort. So we say fn quicksort. We're going to have our array, which will use a mutable array slice. We will have our starting index, which is going to be of type usize, and then we will have our ending index, which is also of type usize. And then if start is less than end, we will say let part or partition is equal to partition the array start and end. And then we will call quicksort again on array start partition minus 1, and quicksort on array partition plus 1, and then all the way to the end. And then here we are going to print out our return our i32 vector. So now we will say array dot toVec. So now we need to implement in our partition. And so we know that we need to pass in a mutable reference to our array slice. We need our start, which is going to be usize, and then we also need our end, which is also usize. And then we need to return a usize because that is where we know our partition, our new pivot was, where our pivot was placed. So we will say let mut I is equal to start, so put the I at the beginning, and then we will put our pivot at the end, and then we will say for j in start equals to end minus 1. So instead of my j being at the end, I'm actually going to put it at the beginning. And then I will say if array of j is less than array of pivot, well, now we want to go ahead and swap, because now we know that our pivot, our j is less than our pivot. So now we want to swap I and j, and now we want to increment I by 1. And then once all of that code is done, well, now we know that our pivot is in the correct spot thanks to this check. We know that everything to the left of where pivot is going to be less than the pivot, and then everything above that index is going to be greater than the pivot. So now we're going to swap I in the pivot and return I, because again, with this check right here, everything that is below I is less than the pivot, and everything above I is greater than the pivot. So now we want to return that index because now we know that that is where pivot was placed, and so now we know that pivot is in the correct spot. And that is what we get returned here. So then we will run quicksort again on everything one below pivot and one above where pivot was placed. So now if we run down here to main and we execute our code, we see that we have 1, 2, 3, 4, 5, 7, and 8. So my implementation, and hopefully yours, which is should be relatively similar to mine. Again, as I said, there are many ways that you can implement this in with different places of putting your pivots. In the previous lecture I showed J being at the end, but to just give you an example of how unique you can get with this, in my implementation I put J in the beginning, so I and J were technically the same. So if you have any questions about my implementation or any questions about your implementation, please feel free to ask them in the Q&A section, and I hope you are comfortable with all the different algorithms that we have gone over in this section on how to do sorting. And in the next section we will begin taking a look at linked list.